Hey everyone. Thought I would do something a little different for my normal pedal videos. This is going to be a tutorial on building a FET mic, and I designed the PCBs and some other stuff for this, but I'm going to be using a capsule, in this case from a company called Miku, which is based in Switzerland, but you can use pretty much any capsule you want. The body I'm using is from a company called Oracle, and you can actually order a kit for them for a FET microphone, but I had some things I wanted to change about it. One thing was it only came with a pad, a minus 10 dB pad, and a single low-pass filter. So the one we're going to be building is going to have a 3-position low-pass filter and a 3-position pad to make the mic a little more versatile. And also, I really like having access to a figure 8 pattern. Helps with doing some stereo recording, and also gives you some really good null spots on the side of the microphone for recording guitar and vocals at the same time. And so what you can do is you can point the microphone capsule at your mouth and the sides of the microphone at the guitar, and it'll null out the guitar, and you'll get more of the vocal and less of the guitar in the vocal mic, but you still get to play and sing at the same time. So what I've got is a microphone that's in one of the... I bought just the body because, again, I've done a new circuit board for it, and I bought a third-party capsule, so I didn't need that. So really all I wanted from them was, you know, the head basket, which I'm going to make some small modifications to, and the body, which consists of a sleeve, has to be painted. I've actually painted another one over here for a tube mic that I'm building, which is a slightly more complicated project that I haven't done a new circuit board for. And inside here, if you got the kit, there would be a transformer in there. But right now it's just the ground, hot, and cold wires from the XLR plug on the bottom. And I'm going to decide on which one of these cinematic transformers I'm going to use. So one of these is 2-to-1, one of them is 4-to-1, and one of them is 8-to-1. And I don't know exactly which one off the top of my head, so I'm going to have to look that up later. But one of these little tiny things is going to go inside this bell here, and its wires will be sticking up out of the top, and we'll attach those to the microphone PCB. I just got in some copies of the circuit board from Oshpark. So these are a public project. I don't get anything for them if somebody decides they want to build this. And a couple people have built at least a couple of these circuit boards. So you're not, if you decide that you want to build one, you're not, you know, getting into something that nobody else has verified. And when we get circuit boards from Oshpark, they're cut off of a panel. So there is a little bit of pointy bits on the side that you can shave off with a file. So I'll do that off camera because you don't need to sit here watching me file things. But the other half of this project is going to be 2 circuit boards. The kit, when you buy it, only has 1 circuit board, and the reason is that, as we'll see in the schematic, it's possible to just use the phantom power to power up the capsule. The capsule has to be externally polarized because that's how these work. And it's possible to just use the phantom power for that, but if you use a separate supply for polarizing the capsule, not only can you get something slightly cleaner, but you can also make something called an oscillator, which will boost the voltage higher than the phantom power that can be supplied for the capsule, and that can make that can improve your signal to noise ratio. It also allows you to tune the capsule voltage so that it's ideal for the capsule that you're using, because some of the capsules that are popular in budget microphones are they can accept like a pretty high capsule voltage, and part of the reason for that is just tolerances. Part of it is just maybe they use thicker material. There's a whole lot that goes into dealing with capsules that I'm not totally up on, but we are using one that's manufactured in China. It's not exactly a budget capsule. It's they've got pretty good R&D. I've been told that this is slightly darker than the capsule it's modeled after. So this is an edge terminated capsule. It's their K12. I've actually got a Ella 251 tube mic clone sitting here that uses a really nice capsule from that I can put links to all this stuff in the description, but the bottom line is that capsule costs over $400, and as much as I love that microphone, I have one and I wanted to build something different. So I ended up with this capsule based on some recommendations on Group DIY. So the thing I'm going to do now is I'm going to pull up the microphone schematic, because I think a lot of people watching this channel are not going to be they're not going to have built a microphone before. So or even if you have and you're not familiar with how a microphone works, we can take a quick look at the schematic. So let me so it looks like my some of my mouse clicks do show up there. So this will be a little weird for me. I'm used to my mouse just working. But let me get the right. So there's two different schematics. We can see that there's an oscillator. That's what's there now, and the microphone schematic. So let's do a review of the schematic. I've opened up the microphone schematic for the board that I used, that I made, and our capsule has two membranes and a backplate. And the thing we care about for the amplifier circuit inside the microphone is the backplate, which is connected to the gate of a FET or a pair of FETs. I actually am building this one with a pair of FETs that are matched, but it can be done just as easily, and actually easier with only a single FET. And this works pretty much how any transistor gain stage works. You've got a supply voltage that comes in up on the drain of the FET, and there's a bias control on the source of the FET. There are other ways to do a bias, but this is the easy one for this kind of microphone. And since a capsule is a really high impedance source, there's this gigantic 1 gigabyte, 1 giga ohm resistor here, holding the gate of the FET to ground. The source is bypassed by a big old 22 microfarad capacitor to get the maximum gain out of it. Even though the FET's main job is actually impedance conversion, so it may be that some people don't care about getting a ton of gain out of the FET, and putting two FETs in parallel certainly increases the signal to noise ratio. But again, the main purpose of the FET is just to perform impedance conversion. So you don't necessarily need a high gain FET here. And in fact, I'm going to be picking FETs that are kind of low gain because I don't really have a use for them otherwise, and it's useful to just be able to put them in in parallel and use them in an application here where they're pretty good at it. The pad switch is accomplished by increasing the Miller capacitance between the gate and the drain of the FETs. And normally FETs have, you know, a couple picofarads of Miller capacitance between the gate and the drain. But if we increase it by, in this case, 10 picofarads and 33 picofarads, which those values are also somewhat related to the capsule we're using, but I haven't really worried about that in the past. I've gotten the results I need just by using these values. And all that does is really, it says, okay, we're not going to amplify some amount of sound. And that's really all the pad is doing, is it's just avoiding amplifying as much as it would without the pad capacitors there. This microphone has a emitter follower, which is in this case it's a PNP transistor, which was it was kind of done because it was a little more convenient on the layout to use a PNP, but you could have used you can use any NPN if you were to rearrange the circuit a little bit. But the reason for the emitter follower is that it gives us a really convenient way to do a high pass filter. So the way this works, and it's an on switch, C3 is in the circuit all the time. And then when the high pass filter switch is in the middle, there aren't any extra capacitors in the way, and if we switch in the 4.7 C4, we get a little bit more bass, and if we switch in C5, the 100 nanofarads, we get full bass all the way down to the limits of human hearing. The highest setting, the one in the middle, is going to be about I think the cutoff was around 150, if I recall correctly. And then the other interesting stuff that's happening all has to do with phantom power and the transformer. It turns out that the transformer I'm using for this project has a center tap, so some of these parts aren't necessary, but normally R5 and R6 serve as this kind of virtual center tap of the transformer, and the transformer carries from the microphone preamp on the XLR pins 3 and 2 the 48 volts for phantom power, and since those signals are out of phase, you want to create a virtual center tap so that you can take the 48 volts without causing your audio signals to get canceled, because this one up here is going to come in and it's going to be flowing one way, and this wave down here is going to be flowing the opposite way. So if you were to just connect one of these to be your power, well, you're going to lose all of your audio. So so that's the purpose of R5 and R6. As I said, in this case, it turns out that since I have a center tap, I don't need those. And then R7 just separates that from the rest of the circuit. Our power comes up here to feed the transistors. And then it's filtered out a little bit, and then the next stage of the circuit that we're interested in is going to be the oscillator. So let's take a look at the oscillator circuit. And the microphone oscillator creates a positive feedback loop on this transistor here, Q1, on this board. And what it's going to do is it's going to feed back only really high frequency stuff back into the transistor, and it'll just go around in a circle and create an alternating current wave that's tapped at C1. Again, notice that C1 is really tiny, 10 picofarads, so it's only letting out really high frequencies. And then C7 and C3 allow us to tap that signal twice so that we can send it off and get two different polarities from it. C7 is actually a typo here. It's another, it can just be a 1 nanofarad, although it doesn't really matter at this point because all we're doing is turning it into DC. So we've got a full wave rectifier on the top, and D3 and D4 allow only the positive going waves to pass. And then all those capacitors, C9, C8, C10, C11, C11 is different, but C9, 8, and 10 are all cleaning up that that DC voltage that we got out of D4. And then the positive voltage is going to go to the front capsule. And if you only have one capsule, well, you really only need the positive voltage. There's no need for the negative voltage. But since we have two capsules, we need to make a negative voltage. And all we do, you'll notice these look identical. All we do is we flip the diodes around to the other way, so now they only pass the negative signal. And then we get a negative polarization voltage. You can control this because you know your FETs and your emitter followers from the other schematic. These draw current, so you don't necessarily know what the voltage at the oscillator pad here is going to be. It turns out that it's usually around 35 volts, but it could be less. And particularly as you bias the FET differently, it can draw more current, and thus it's going to take more power from here. So that is the reason that we need a trim pot on our oscillator's transistor, because then we can control exactly how much voltage we get out here. And some capsules you might not care too much. I shot for 60 volts on my FET builds, but I have another capsule that prefers a lower voltage. It prefers 50 volts. So I definitely want to be able to use the same oscillator board for multiple capsules if I can. The last couple things here, C11 is used in some of the figure 8 pattern setups where you want the figure 8 pattern to have less gain than some of the other patterns. So what C11 does is it just, you can see that if you're feeding both membranes on the capsule and they've got waves going in the opposite direction, well, if some of the signal can pass through C11, they're going to cancel a little bit of their signal. And the last thing over here, these are just some capacitors that are important for filtering out power. We want the capsule voltage to be as smooth as possible, so it's not always good enough to do these. We also want to make sure that the oscillator itself is stable, and that's why C12 is actually the highest value capacitor in the entire circuit. Okay. So next we'll take a look at some of the board stuffing and get started on actually building the mic. So one thing that's not shown on the schematics is how the polar patterns work. So I've opened up Eagle and we're just going to work this out. It's not something that you need to wire on the board. It's all going to be wired on a switch. So we know that since we have 3 polar patterns we're interested in, that's Omni and figure 8 and cardioid, that we're definitely going to need a switch that has 3 positions. So we need an on-off on switch. And it could be, I mean, I guess theoretically it could be on, but there's not a way to, the easy way to do this is just going to be on. And the pattern for this is kind of taken from the U87AI. And it's going to be done almost exactly the same way. So we know that we have a positive voltage, and if we look at the oscillator schematic, we just to remind ourselves, so there's our positive voltage, so we have that to play with, and then we need a negative voltage because that's the other voltage that we have to play with. So these are the only things that we have that we can really do anything with. And let's go ahead and connect those. And then the input, of course, is just going to be the membrane. So let's take an input pad and rename this just so we can remind ourselves. So that's now called the rear membrane. So what happens here? Well, when the rear membrane gets pulled up to the positive voltage, then when we look on our our oscillator, so when it's pulled up to the positive voltage, that means that both the front membrane and the rear membrane are both getting the same voltage. So they're gonna be in phase signals, and we're not gonna get any cancellation based on where those two membranes pick up sound, and that's gonna give us an omni pattern. We're not gonna get any cancellation. Now let's see what happens when we pull down to the negative voltage. There we go. So let's pull the rear membrane down to the negative voltage, and now we can see that we're gonna have a signal on the rear membrane that's out of phase with the signal on the front membrane. So this one comes in, so our rear membrane here is going in one direction, and the front membrane's going in the opposite direction. And what happens? Well, the sides are gonna get signal from both membranes, but that signal is going to be out of phase. And what happens when we have signals that are out of phase? Same thing that happens, on the XLR plugs 3 and 2. They're out of phase. Well, why are they out of phase? It's because when that signal's traveling along the long mic cable, if any noise is picked up, it's just canceled because they're out of phase. So we know that canceling the signal gives us, or we know that out of phase signals, when they get mixed together, they cancel each other. And what happens? We get a figure 8 pattern because now the sides of the microphone are going to cancel each other. And the last thing we have to deal with is we said, well, we've got 3 patterns, right? We've already dealt with omni, that's up here. We've already dealt with figure 8, that's down here. Well, how do we get cardioid? Well, it turns out the cardioid is accomplished by just making the rear of the capsule not do anything. And so when the rear membrane is set in the middle, none of the, you can imagine none of these are connected when we're set in the middle with the switch. Then the rear membrane ends up going to ground. And why does it go to ground? Well, it's just not getting any voltage whatsoever. And so any voltage that it had, any voltage that it picked up that was positive, or any voltage that it picked up that was negative, when sound waves hit it, it's just going to discharge that voltage. It's going to wiggle against the back plate, and any positive or negative voltage that was left on the rear membrane is going to dissipate, and then it'll be sitting at ground. And once it's sitting at ground, then the rear membrane can't produce a voltage when it wiggles against the backplate, and that gives us cardioid by disabling the backplate.